Hello, the title of this lesson is Continuous Functions on Interval. And the plan here is to talk about the boundedness theorem and extreme value theorem. We'll also talk about the intermediate value theorem as well as its corollaries. As a starting point, let f be a function between I and r, where I is an interval on the real line. We say that such a function is bounded if its range its range, which is the set of all f of x in R such that x is in I, is a bounded subset of the real line. As an illustration, let f be a map between 0, 1 into the real line such that f of x is equal to 3x plus 1. And let's see that this function is indeed bounded. In fact, for any real numbers x in between 0 and 1, you will agree that x is in between 0 and 1, and consequently 0 is less or equal to 3x, which is less or equal to 3. And this implies that adding 1 on each side gives us that 1 is less or equal to 3x plus 1, which is less or equal to 4, right? So the range of this function is the closed interval from 1 to 4, which is clearly a bounded. This interval is bounded on the real line. Alright, so the boundedness theorem is stated as follows. Let I be a bounded closed interval, and f is mapping some interval I into R is a continuous function. Then the conclusion here is that f is bounded on the interval I. Okay, so the proof is as follows. Suppose by contradiction that f is unbounded on I. Let's say, for example, suppose that f is unbounded above. Then the following holds true. First, since 1 is not an upper bound for the range of f, which we denote R of f. Sometimes people denote this im of f, same thing. Then there exists some elements which are called x1 in I, such that f of x1 is greater than 1. And again, since 2 is not an upper bound for the range of f, then there exists some element x2 in I, such that f of x2 is greater than 2, and we can keep going in this fashion. So since k is not an upper bound for the range of f, then there exists x sub k in I such that f of x sub k is greater than k. So we proceeding in this fashion. We construct a sequence of real numbers xk when k is going from 1 to infinity in I such that f of xn is greater or is strictly greater than n for any natural number n. So consequently, it follows that the limit of f of xn as n is approaching infinity is going to be infinity. Now, since I is bounded, then the constructed sequence xk from 1 all the way till infinity is a bounded sequence, and by the Bolzano-Weierstrass theorem, xn or xk conforming to xk has a convergent subsequence which I'll call x and k. Now let's so in fact this sequence is bounded and it has to be convergent, and let L be a real number such that f such that the limit of x and k as k is approaching infinity is equal to L. All right, then what will happen is that since f is continuous, then the limit of f of x and k as k is approaching infinity must be equal to f of L. However, the subsequence f of x and k, when k is going from 1 to infinity, is diverging to infinity. As a result, so this is a contradiction. This gives us the desired contradiction. Okay, so as a corollary, we have the following. Let I be a closed and bounded interval, and let F be a map taking I into the reals. Let this be a continuous function. Then given a set A, which is the set of all f of x such that x is in I, the supremum of A and the infimum of A both exist as real numbers. So in other words, the supremum, the sup, and the inf of A are finite. Okay, alright, so any function which is continuous on a closed and bounded interval will, if we look at the range of this function, then this range as a subset of the reals has a finite supremum and then a finite infimum. And next we have the extreme value theorem, which we state as follows. Let I be a bounded closed interval, and let F be a continuous function from I into R, then F attains its supremum and its infimum. So in other words, there exist, I'll call this x sub star and x sub star in I, such that f of x sub star is the infimum of the set of all f of x such that x is in I, and we will call this, in fact I will denote this inf of f sub I, and f x superscript star is equal to the supremum of the set of all f of x such that x is in I, and we will denote this sup of f in I. Alright, so as an illustration before the proof, suppose we have a function on some closed interval. So this is I on the real line, and our function behaves sort of like this. Okay, then you can find some x subscript star here such that this number here is the infimum f of I, and then you can find another number x superscript star here, such that the sup of f I is located here. Okay, again, it is important here for the interval I to be closed and bounded, so we may not be able to remove those assumptions. Okay, but under those two assumptions, then this result is always true. So for the proof, let little m be the infimum of f on I, and big M be the supremum of f on I. So since okay, by definition, there exists a sequence f of xn with xn in I, such that the limit of f of xn as n is approaching infinity is equal to m. Okay, all right, then now since xn is in the set I, it is a bounded sequence and as such it has a convergent subsequence, which we shall denote x and k according to the Bolzano-Weierstrass theorem. Okay, so now let's x and k, let's the limits of x and k as k is approaching infinity be equal to x sub star. Then it is the case that x star must be an element of I, because I is closed and bounded. So then next, since f is continuous in x is continuous at x star, then the limit of f of x and k as k is approaching infinity would be equal to f of x star. Okay, But we have seen that this but on the other hand, we know that the limits of f of x and k, as k is approaching infinity, is m. Okay, therefore f of x and f of x star must be equal to m. Okay, and the proof for little m, the proof that there exists some x star in I such that f of x of star is equal to little m, which is the infimum, follows similar argument and is omitted. Let's consider the following two examples. So first, let's f of x, let f be a map between 0, 1 into the reals such that f of x is equal to 1 over x. So notice here that the interval 0, 1 is not closed. It is bounded, but it is bounded. Then if we consider the image, the range of f, which is the set of all f of x such that x is in 0, 1, that will be the set of all 1 over x such that x is in the open interval 0, 1. And we observe that if x is in between 0 and 1, this implies that 1 over x is always bigger than, is greater than 1, right? And furthermore, the supremum of the sets f is not defined. It's not defined as a real number. Okay, so our previous result, which says that if a function is continuous on a closed and bounded interval, then it reaches its supremum as well as its infimum. We cannot remove the condition that the interval is closed, right? Here's an example of an interval which is bounded, but which is not closed, and the theorem does not hold. Okay. On the other hand, if we consider, let's suppose that f is between the reals and the reals such that f of x is equal to x. Clearly, both of these functions, 1 over x is continuous and x is also continuous. Clearly, f is continuous on R. However, the range of f, which is the set of all x's such that x is a real number, is unbounded. So the infimum of R of f and the supremum of R of f are not defined as real numbers. So in other words, again, the condition that the interval I is bounded is also an important condition, and we cannot dispense with those two conditions easily without violating the theorem. Okay, and finally, if we consider if we let f be a function from, let's say, 0, 1 into R, such that f of x is equal to sine of cosine of x squared, by the properties of elementary continuous functions, f is continuous on 0, 1. Therefore, there exists some x sub star such that f of x sub star is the infimum of f on I, and there exists some x star in 0, 1 such that f x star is the supremum of f on I. Okay, so although these numbers can be really hard to find, we know that they exist, and this is due to our previous result. Our next theorem is the intermediate value theorem. Let I be an interval, and let f be a continuous function from I into R, and let A and B be two elements in I, such that A is less than B, and suppose, for instance, that f of A is less than f of B, then there exists some lambda. Then for any lambda in the open interval f of A to f of B, there exists a point C in A and B, such that f of C is equal to lambda. So as an illustration, let me put this on the side. Suppose this is A and B, and this is f of A, and let's say f of B, here, and if we pick any lambda here, and of course there are many possible points that may map to such a lambda. There are many points that may map to such a lambda, and so the point is there exists a C in this interval, which is taking such that f of c is equal to lambda. Okay, so the proof is as follows. Let A be the set of all x in A and B such that f of x is less or equal to lambda. Then clearly C A is not empty, since A is in big A, because f of A is less or equal to lambda, right? So by the completeness axiom, the supremum of A exists as a real number. Okay. So I will let C be the supremum of our set A. Then we will prove that it is the case that f of c is equal to lambda. So as an illustration, if we consider so we are looking for all f of x less than lambda, and this will correspond to, right, this set here, right? And then we want to show okay, so we want to show that this C is a supremum. So here is our A. Our set A is this. This is for just our illustration. It's not part of the proof, but this will help you understand the proof. Okay, and then we want to show that f of c must be equal to lambda, as shown here. So first, let us prove that f of c is less or equal to lambda. So since c is the supremum of A, then there exists a sequence. One can find a sequence xn in the set A, such that the limits of xn as n is approaching infinity is going to be equal to c, and since f is continuous at x is equal to c, then it's clear that by the sequential criterion of continuity, then the limit of the image sequence f of xn will converge to f of c. Okay, but we know that xn is an element of A for all natural numbers n. Thus f of x sub n must satisfy the inequality, the following inequality, for any natural number n. Okay, now we will use the fact that if we compute now the limits of so then the limit of f of xn being equal to f of c, then okay, since the limit of f of xn as n is approaching infinity is equal to f of c, then it is clearly the case that f of c is less or equal to lambda. Okay, now secondly, we will prove that f of x is greater or equal to lambda. And again, since c is the supremum of A, and then for any given any natural number n, c plus 1 over n cannot be an element of A, right? Otherwise we will have that c plus 1 over n is less or equal to c. So thus f of c plus 1 over n must be strictly greater than lambda for any natural number n. Now note also that the limit of c plus 1 over n as n is approaching infinity is equal to c, and by the continuity of f, at then we know that at c we know that the limit as n is approaching infinity of f of c plus 1 over n is going to be equal to f of c. Now since f of c plus 1 over n is strictly bigger than lambda for any natural number n, we have that the limit of f of c plus 1 over n as n is approaching infinity is greater or equal to lambda. Hence f of c must be greater or equal to lambda. Alright, so in summary, we have that lambda is less or equal to f of c, which is less or equal to lambda. Therefore the limits therefore f of c must be equal to lambda, and this completes the proof. as an example, let f be a function between r and r such that f of x takes the form negative x squared plus 1. Then we verify that f of negative 1 is negative 1 plus 1, which is 0, and f of 0 is equal to 1. So given any lambda, or let's say given lambda, which is 1/2 in the open interval 0, 1, there exists some number c, right, in between negative 1 and 0, such that f of c is equal to 1/2. In fact, as an illustration, we'll have the following. So we compute in between negative 1 and 0, and we get 0, 1, and then we pick lambda to be here, right? And clearly you can find some c in between negative 1 and 0, and precisely here, precisely for this example, c is negative square root of 2 over 2. Okay. Another example could be the following. Let f of x be x minus 1 e of x, and verify that f of 0 is negative 1 e power 0, which is negative 1, and f of 1 is 0, right? Okay, now next, let lambda pick a number in between negative 1 and 0. Let's say negative 1/2 or negative 2/3, whatever. Take negative 2/3 in negative 1 and 0. Then there exists some c in the closed interval 0, 1, such that c minus 1 times e c will be equal to lambda, which is negative 2/3. So although this equation can be really hard to solve, it can be really hard to find such a c, we know that such a c exists. There exists such a number which satisfies this criteria. Corollary: location of root. Let f be a map between from AB into the reals, which is a continuous function. If f of a is negative and f of b is positive, or vice versa, then there exists little c in a and b such that f of c is equal to 0. And as an illustration, we have the following. This is a and this is b. Suppose we have a function like this. Okay, so here f of a is negative and here f of b is positive. Then there must be a place c, because the function is continuous. There must be a place c at which the function is actually crossing the x-axis. Okay, all right. So the proof goes as follows. According to the preceding theorem, for any lambda in between f of a and f of b, there exists some c in between a and b such that f of c is equal to lambda. In particular, letting lambda be equal to 0, there exists some c in between a and b. Since I already used c, let me use c prime, such that f of c is equal to 0. So I remark here that this corollary is called the location of roots, because c represents a root, roots of the equation f of x is equal to 0. Thus, this corollary ensures that if f of a and f of b have opposite sign, then between a and b there will be a root c of f of x. So let me write this. This corollary states that if the product of f of a and f of b is negative, then there exists a solution for the equation f of x is equal to 0 located in the interval a to b, and such a number, such a solution is called a root for a root of f of x. Example, let f be a map taking the closed interval 2 to 4 into the real, such that f of x is equal to x squared minus 4x plus 3. So we verify that f of 2 is 2 squared minus 8 plus 3, so that'll be 4 minus 5, which is negative 1, and f of 4 is 16 minus 16 plus 3, which is 3, which is greater than 0. So by the previous result, there exists a solution C for the equation x squared minus 4x plus 3, and such a solution C must be located in between 2 and 4. So as an illustration, the graph of this function looks like this. 1 and let me see, does this work? You get 1 minus 4, that's negative, yeah, that's right. And we are located in between 2 and 4. Looks somewhere like this. And there exists C. This is y equal to x squared minus 4x plus 3, and there exists C in between 2 and 4, such that C is a root for this equation. All right, so a corollary lets I be a bounded closed interval and f a continuous function. Then the range of f, which is also denoted f of I, which is the set of all f of x such that x is in I, is also bounded and closed interval. So as an illustration, suppose we have our interval, which is perhaps very crazy. It's behaving like this. Well, let me maybe like something like that. Okay, all right. And this is I. This is the interval I. Then one can see that the range of the function will be all of this. This will be f of I, and you can see that f of I is also, in this example as illustrated here, it's a closed and bounded interval as well. Okay. So for the proof, let's little m be the infimum of f of I, and let big M be the supremum of f of I. Okay, then we want to show that f of I, the range of our function, is the closed interval m to m. Okay, so first we have that little m is less or equal to f of x, which is less or equal to f of big M for any x in I. Hence, f of I must be a subset of this closed interval, right? Because any elements in, so in other words, x is in f of I implies that f of x is in the closed interval m to m. Now, secondly, the extreme value theorem guarantees implies that there exists x, let me use x1 and x2 instead, x1 and x2 such that f of x1 is gonna be little m, and f of x2 is gonna be big M. Thus, m and m are elements of f of I, which consists of all f of x. Is the range of our function. So little m and big M are in the range of our function, and by the intermediate value theorem, there exists little c in big I such that f of c is equal to lambda, thus lambda is also in f of I. So any lambda between little m and big M belong to f of I, to the range of our function, and this implies that the interval m big M is a subset of f of I. Okay, so So since we have mutual inclusion, we obtain that f of I is the closed interval M. And this is the proof of our corollary. Let f of x be x squared sine of x, where f is taking the real line, let's say 0, 1, into the real line. Then from our previous results, the range of f, which is f of 0, 1, which again is really the set of all x squared sine of x, where x is sitting in between 0 and 1, is a closed and bounded interval. And our next result, which is a corollary, is about the preservation of intervals. So we have a similar result which says that let I be an interval and f a map between I and R. And by the way, in my previous example, the reason why the result follows is because I forgot to say that f is continuous. Okay, and let f be a map between I and R, which is continuous. On I, then f of I is also an interval. As an illustration, if we let f go between 0 to infinity into R, such that f of x is, let's say, the natural log of x, then the image, the range of our function is all real lines, right? Which is, this is an interval. If we were to say, if we were to consider f between R take away 0 into R, where f of x is 1 over x squared, then the range of f, which is f of R take away 0, consists of all numbers of the type 1 over x squared, such that x is not 0, and that's 0 to infinity, which is also an interval.